The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Last time, we went through the same arguments that Maxwell and Boltzmann did to understand the microscopic origin of the ideal gas law, PV equal nRT. And we saw how Maxwell had decided that, or had hypothesized, that, gee, you know, the pressure of a gas on the walls of some container, hey, you know, if the molecules were moving and they collided onto the walls, that pressure must be due to the individual impacts of the wall, of the molecules on the wall. That must be due to the change in the momentum of the wall when the molecules slammed right into it. And that change in momentum over some change in time is this force. That force divided by the total area is the pressure. And it was using that argument that we came up with an expression, just like Maxwell did, for the pressure times the volume. And we see that we were able to write it in terms of the velocity of the molecules that were moving in this gas. Well, that's very nice, because if we have this theoretical expression, P times V, and we know experimentally that P times V equal nRT, well then, if this theory is correct, well then this quantity, Nm average of the velocity squared over 3, hey, that better be equal to nRT. Or solving for what we call the root mean square velocity, that better be equal to the square root of 3RT over m. So that kinetic theory made a prediction for what the velocity ought to be. And it, of course, took another 100 years before somebody could measure that. And, of course, it is correct. But what's interesting here is that this model gave us an understanding for what temperature is. Temperature, right, is a measure of the speed of the molecules in the gas. It is also, as we saw last time, a measure of their kinetic energy. We saw that the kinetic energy is 1/2 m average of the velocity squared. We put in our result from kinetic theory. That shows us that the average energy is 3/2 RT. Temperature is a measure of the kinetic energy of these molecules in the gas. All right, so for the first time, there was a microscopic understanding of what temperature was. Okay. Now, what we looked at also last time is we looked at the Maxwell-Boltzmann distribution of velocities or speeds. And we talked about this particular functional form, how there was this quadratic dependence right here at low v because of the v squared here, and then an exponentially decaying tail. All right? There were two parameters, the mass and the temperature. We talked about that last time. But of course, if there's a distribution here of speeds, where this distribution is a probability of finding a molecule with a particular speed between v and v plus dv, well, then there also has to be a distribution of energies because the velocity is related to the energy. Okay, so what do we have to do? Well, we got to take that Maxwell-Boltzmann speed distribution and change the variable to energy. And we know how to do that. We know how to equate those two distribution functions, and using the Jacobian of the transformation that we talked about last time, hey, we can calculate what the energy distribution is. So this, f of v, is our Maxwell-Boltzmann energy distribution. It's the probability of finding a molecule with a kinetic energy E to E plus dE. All right? It also has a decaying exponential term here with the energy in the argument. And it's multiplied by e to the 1/2. let's take a look at what that distribution function looks like. Here it is. Notice, as we learned last time, that the energy has nothing to do with the mass of the particle. The only parameter that is important is the temperature. So at a given temperature, all particles, doesn't matter what their mass is, they have the same energy. So all particles at 600 degrees Kelvin have a Maxwell-Boltzmann energy distribution that looks like this. There's a very rapid rise in that distribution function, unlike the velocity distribution, which increased as v squared, right? It peaks rapidly, and then there's an exponentially decaying term in the energy. At 1500 degrees Kelvin, hey, the energy distribution looks like this, right? The energy of the molecules has increased. So since this is a probability, right, and the area under these curves has to equal to 1, well, if the energy goes up, that is, we have more molecules out here with higher energies, well, then this maximum value for the probabilities, that's got to go down because we got to keep the area under that curve equal to 1, since this is a probability. So what we see here as we raise the energy, what we see is that we have more and more molecules here with high energies. There are not a lot of them, but there are some, and they're going to be really important in the example I'm going to show you in just a moment. All right, so average energy at 600 Kelvin, just 3/2 RT. It's 7.5 kilojoules per mole. Average energy at 1500 Kelvin, it's 18.7 kilojoules per mole. All right? Okay, but now I want to show you an example of the importance of this Maxwell-Boltzmann distribution function for energies to chemical reactions. All right? The importance of it in making some kinds of chemical reactions actually proceed, actually work. All right? And so the example is going to be this reaction. This reaction is called the steam reforming of natural gas. It's the reaction of methane plus water. Hey, natural gas is mostly methane. But this reaction of methane and water makes CO and hydrogen. Now, it turns out that this reaction does not work in the gas phase. That is, if you have a methane molecule and water molecule collide, hey, they're just going to collide, bounce apart, and go in their opposite directions. They're not going to make CO and hydrogen. And so what you have to have in this reaction to make it go is you have to have a catalyst. That catalyst is going to be a nickel surface. A catalyst is something that will lower the activation energy barrier by changing the mechanism of the reaction so that the reaction can proceed. So in this case, what happens is that the methane and the water impinge on this nickel metal catalyst. And the methane and the water, they decompose. They fall apart to their elements on that nickel surface. And then once you have carbon, hydrogen, and oxygen on that nickel surface, well, then the atoms rearrange and they come off as CO and molecular hydrogen. So that nickel surface is a catalyst, and we call this a catalytic reaction. In particular, we call it a heterogeneous catalytic reaction. It's heterogeneous because the catalyst is in a different phase than the reactants. The catalyst here is a solid. The reactants are gases. A homogeneous catalyst is one in which the phase of the catalyst and the reactants is the same. All right, so this is a heterogeneous catalytic reaction. Well, it turns out that this reaction here is really an important reaction from the standpoint of the production of hydrogen. All of the hydrogen that you use, you know, if you're doing a laboratory experiment and you go get a tank of hydrogen, hey, that hydrogen was made by this reaction, by reacting methane and water to form that hydrogen. All of our commercial sources of hydrogen come from carrying out this reaction. So for example, if you're in the business of ammonia synthesis, right? Ammonia synthesis, which is taking hydrogen and nitrogen to make ammonia, and this is also carried out on a iron surface. This is another heterogeneous catalytic reaction. And ammonia, of course, is a starting material for lots of chemicals, in particular fertilizers. So if you have an ammonia plant, hey, right next to the ammonia plant, you've got a steamer forming plant to make the hydrogen to feed into this reaction. All right? And another place where this is useful is in the methanol synthesis. That is, you can take hydrogen and CO and on a copper zinc oxide heterogeneous catalyst to make methanol, starting point then for gasoline, which now is certainly economically feasible. Right? Okay, but it turns out that this reaction here, this reaction is really a hard one to carry out. Despite the fact that nickel is a catalyst for the reaction and makes it go, the reaction still has to be carried out at very high temperatures. 1500 degrees Kelvin is very high temperature. It also needs very high pressure. So one of the reasons why we don't have a hydrogen economy is because it's so difficult to make hydrogen. Can be done, and it is done in all of the commercial processes that I mentioned to you. But it's still hard. It's 1500 degrees Kelvin, high pressures. The question is, why is it so hard? Why is there this barrier here? Why do we need to raise the temperature of the gas in order to get this reaction to go? Well, let's take a look at that. What there exists here in this problem is a barrier, what's called an activation energy barrier, to making the reaction go. And it turns out that this activation energy barrier is really in the very first step of the reaction, which is pulling the methane apart, pulling that first hydrogen atom off of the methane molecule. So what I represent right here is the energy of the reaction as a function of the reaction, and the reaction here is just the first step. It's taking methane gas, pulling the hydrogen off, so that you have a methyl radical stuck to the surface, and you have a hydrogen atom stuck to the surface. It's just breaking that first CH bond. Right? And what you can see here is that you have to put, I wrote 50 kilojoules of energy into that reaction in order to make it go. You have to put that 50 kilocalories of energy in first before you get any energy back. You can see this is exothermic, but you got to put this energy in order to get that reaction to go. Well, how do we know that? Well, let me back up a minute. So here's where the Maxwell-Boltzmann energy distribution is important. What I did is I took those Boltzmann energy distributions that I plotted for you at 600 Kelvin and 1500 Kelvin, and I turned them on their side, right? So this is essentially equal to the probability of finding a molecule at a particular energy versus the energy. And here's the Maxwell-Boltzmann distribution at 600 degrees Kelvin. Hey, it's peaked to very low energies. And if you look here in this Maxwell-Boltzmann tail, well, there are not very many molecules that have enough energy to get over that barrier. However, if we raise the temperature of the gas to 1500 degrees Kelvin, well, then now you can see that there are more molecules here in the high energy part of this tail. Right? And it's these molecules at these high energies that actually can get over this barrier to dissociation of the methane molecule. Now, there are not many of those molecules with high energy, but there's some, and that's important. Because what happens is that when they have enough energy, they react and they leave. And then this Boltzmann distribution reequilibrates. Right? If the high energy molecules leave, well, then there are lots of collisions here which kick some more molecules up to the high energy part of the tail, and they react. And so it works. Okay? So that's why it's important. But now, how do we really know that there's this barrier here to the dissociation of methane? And why is there this barrier? You know, what is the physical origin of this barrier to pulling this CH bond apart? Okay? Well, one way we could know that there was this barrier there for sure is to do the following. If we had a way to take methane gas, and make it have just a single energy, and not the Maxwell-Boltzmann distribution of energies, which have lots of different energies in them. You saw how broad those curves were. But if we had a way to make methane with just, say, energy E sub 1, whatever that is, we could then take those molecules with just those energies, aim them at this nickel surface, and see if the methane fell apart. And if it didn't, then we would prepare molecules at some higher energy, see if they fell apart. If they didn't, we'd go to higher energy. We'd keep going until we get to the top of the barrier, right? Well, how do you do that? How do you make molecules with a particular energy? Because I just showed you a Maxwell-Boltzmann energy distribution at 300 Kelvin, 600 Kelvin. Hey, there are a lot of energies present. How do we make molecules with just one energy? Well, we got a way to do this. And we do this using some beam techniques and high-pressure adiabatic expansion. And basically, the way it works is this. What we're going to do is we're going to take a tube here, and that tube's going to have a high pressure of methane in it. And then we're going to punch a little hole in that tube. And this tube is actually sitting in a vacuum. So we're going to expand the methane from that tube into the vacuum. We're going to squirt it out. It's going to come a beam of molecules. But in this kind of expansion, when you expand a gas from high pressure to low pressure, this expansion is called an adiabatic expansion, which means the gas cools. I'll explain that in a moment. But the adiabatic expansion, I'm going to talk a lot about in 560. And if you're a chemical engineer, you'll talk even more about it past 560. Okay? But here's how it works. It works, you take these molecules, squirt them out. Because the pressure right here is so high, what happens is there are lots and lots and lots of collisions. And so you can imagine if you've got some slow molecule just kind of lumbering along, and a fast one comes and hits you, right? Well, what's going to happen is you're going to speed up, and the fast one is going to slow down. And if you keep doing that again and again and again, hey, all the molecules are going to end up with the same energy or the same velocity, right? If you've got so many collisions, after a while, they're going to all have the same velocity or the same energy because one gets sped up, one gets slowed down. Hey, they're all going to end up with the same energy. And that's what happens. That's how we make a beam of molecules, a source of molecules with the same kinetic energy. And basically what's happening then is that before the expansion, just look at this curve. Here's a Maxwell-Boltzmann distribution of velocities, right? It's broad. But after this expansion, here's the distribution. It's really pretty narrow. If you put a temperature to that distribution, you might find it's, hey, 1 degree Kelvin. You can really make molecules with a single or very narrow distribution in energies. All right, so that's what we do. We make those molecules with this energy, E sub 1, and then we got some more tricks for changing those energies in a controlled way. And we just keep cranking those energies up and watch to see when the methane falls apart. All right, and so you get data that kind of looks like this. This is a dissociation probability of the methane as a function of its energy. This is in kilocalories per mole. At some point, say right about here, 15 kilocalories per mole, the dissociation probability skyrockets. All of a sudden, you're at a high enough energy to get that methane to fall apart. So this tells you exactly where that barrier is, all right? Okay, but now the question is, why is there this barrier? You know, physically, why is there a barrier to pulling the hydrogen off of the carbon when that methane molecule comes close to the surface? Well, the reason is this. In order to break the carbon-hydrogen bond in methane, in order to have enough energy to break that bond, what you need to do is you need to simultaneously form a nickel-carbon bond and a nickel-hydrogen bond. So in other words, when this methane molecule here, when it comes into some nickel surface very slowly, because that methane is tetrahedral and the carbon is kind of hidden in the center, when it comes into your nickel surface slowly, well, hey, the hydrogens interact with the nickel, but the carbon doesn't get in close enough to the nickel to start to form a nickel-carbon bond. But now, if you speed that methane molecule up and you really ram it into the surface, well, hey, upon collision of the molecule with the surface, the hydrogens are pushed back, the carbon gets in close enough to the nickel to start to form here this nickel-carbon bond. You form a nickel-hydrogen bond, and hey, now you can break that CH bond. So we call this flat chemistry. And the barrier there to that reaction, that barrier to the reaction physically is the amount of energy that you have to put in the molecule to push those hydrogens back, you know, to bend those hydrogens back, to distort this methane molecule. Once you do that, reaction goes. You're on a roll there. It goes, all right? So that's the physical origin of this barrier here to the dissociation of methane. You need to put enough kinetic energy into those methane molecules in order to get over that barrier. And what we do that on a practical scale by raising the temperature of the gas. But on a microscopic scale, this is what's happening. Okay. But then, well, you can imagine that my students and I did this experiment 15 years ago, all right? But then we said, well, okay, if this barrier here is the energy required to deform that methane molecule, well, then we should be able to do this experiment, right? This experiment is the following. We're going to take our nickel surface here, and we're going to lower the temperature of the surface to 47 Kelvin. At that temperature, what we can do is we can freeze a layer of methane on the surface. We call it physisorb, a layer of methane on the surface. It'll just stick there, all right? And then, well, you know, if this barrier is the energy required to deform or distort the molecule, well, then in principle, I could take a hammer, right, and pound that molecule into the correct shape for the transition state that leads to dissociation. Sounds like a simple idea, and it is. Except that we can't really take that hammer, but we can take an argon atom. So we can freeze the methane onto the surface, and now we come in with an argon atom. Hey, that's just a big ball, or a xenon atom, or a krypton atom. And we know how to accelerate xenon or krypton. We don't accelerate it too much, 50 kilocalories, 70 kilocalories per mole, something like that. And then we can bring it in. And what happens is that the impact of the collision on that methane causes that methane molecule to compress, distort, gets it into the configuration of the transition state that leads to the methane falling apart. Okay? And so you get the same result, right? The question there is just getting the energy into the molecule to actually distort it, to deform it, so you can make the nickel-carbon bond and the nickel-hydrogen bond. That's the key. So my students and I, after we spent many years doing this experiment, spent a lot of money on this experiment, we said, well, now we have proven for sure that when a bug flies into the windshield of your car, you do get the same result as if you hit the bug on the windshield of your car with a bug swatter. That's what we did. Okay, so this is an example of one chemical reaction for which we know the physical origin of the barrier. There are very few chemical reactions for which we know anything about the physical origin of a barrier to a reaction. Okay. But now, what I want to talk about is go back to kinetic theory, because the kinetic theory is going to allow us to calculate a couple of more quantities that are of interest to us. And one of those quantities is the collision frequency. And let me just write that on the board here. What I'm going to want to calculate is something called Z1, or I'm going to call it Z1. And it's the number of collisions that a molecule makes in a gas per unit time, and our unit time is going to be seconds. All right? This is the collision frequency, or this is the collision frequency of a single molecule in a gas. Okay. So how am I going to calculate this quantity using the kinetic theory approach that we've been talking about? Well, what I'm going to do is this. I'm going to take some gas, and that gas here is represented, the molecules in that gas are represented by these blue circles right here. All right. They have a diameter d. And then within that gas, I'm going to imagine this lighter blue cylinder. So that cylinder is an imaginary construct. We're going to use it to calculate this collision frequency. And what it's going to be is the collision volume. All right? I've set the diameter of that cylinder to be equal to 2 times the diameter of the molecule. So I've set this up right. And the bottom line is that all of the molecules that instantaneously happen to be in this cylinder, when a molecule comes through, all of those molecules are actually going to be hit, are going to suffer a collision with another molecule. And I'm going to use that, the number of molecules in this volume, to calculate this collision frequency. That's what I'm going to do. Okay, so snapshot in time, those molecules are frozen there, except there's one smart alecky molecule that comes cruising on through. There he comes. Bam, bam, bam. Hits these 3 molecules here, because they're more than halfway into that collision cylinder. All right? Okay, now, what I know is this smart aleck was moving at some average velocity that I'm going to call v bar. In a time t, this molecule, since it's moving with an average velocity v bar, in a time t, it's traveling a length v bar times t, right? Velocity times time, that's going to give you a length. And so I'm going to set for convenience, this time equal to 1 second, because that's going to be my unit of time. I want to do this per second. I'm going to set this equal to 1 second. So therefore, this molecule is going to travel a length v bar in 1 second, and that's the length that I'm going to make the collision cylinder. I'm going to make that collision cylinder be v bar long. That's the distance traveled in 1 second by the smart aleky molecule. Okay? Okay. So now, what all I have to do is I've got to take the volume of this collision cylinder and multiply it by all the molecules that happen to be in that volume at that particular time. All right? Because that volume represents the volume swept out in 1 second by this smart aleky molecule. Okay. So what's the volume of the cylinder? Well, I set the diameter to be equal to 2d. The volume of the cylinder is the area, cross-sectional area, times the length. That cross-sectional area then is pi r squared, but r here is equal to d, just to make it confusing. Right? So the area is pi d squared. The length is v bar, so that's the volume of the cylinder, pi d squared v bar. Okay, so we got the volume of the cylinder. Now what we're going to need to know is the density of the molecules in this cylinder. Well, the density of the molecules in the cylinder is the density of the molecules in the gas, right? I mean, the cylinder isn't special. The cylinder is an imaginary construct that I put in there to help me calculate the collision frequency. So, I need the density of the molecules in the gas or in the cylinder. The density of the molecules I'm going to set as equal to n, the total number of molecules in this volume, divided by the volume of the gas. Now I'm going to call that rho. N over V is going to be equal to rho. That's the number of molecules per cubic meter. That's the density of the gas. This is the symbol that I'm going to use from now on for density, defined as molecules per cubic meter. Well, then the collision frequency is simply going to be the density of the molecules times the volume of the cylinder. Right? So the collision frequency Z1 here is this volume of the cylinder, pi d squared v bar, times the density. Why? Because every molecule in that cylinder, I set it up so that every molecule in the cylinder would suffer a collision. And that cylinder is the length that a molecule travels in 1 second. All right? So there's the density times the volume. Hey, the meters cubed disappears. And what I've got left is rho, the density, pi d squared v bar. This is collisions per second. So I've got my collision frequency. This is the single molecule collision frequency. This is the frequency of collisions that one molecule makes with the other gas molecules. Okay, that's important. We're going to do a different kind of collision frequency in just a moment. All right, but now it turns out there's another factor here that I have left out because I haven't done as sophisticated an analysis as I could. And that is that I made the assumption in my picture before that all the other molecules were frozen in time, right? And that there was only one smart aleck that was moving around, cruising through, all right? The reality is they're all moving. And what I really have to do is I have to take into account the relative velocities of the molecules, the relative speeds. I can do that. There's a little more sophisticated analysis in doing that, but I could do that. And if we do that, this makes a difference of the square root of 2. All right? So I'm just going to put that square root of 2 in there right now. Later on, you will be able to see where that comes from in a later course. All right, so that actually is the collision frequency of a single molecule in the gas. Okay. Now, I'm also interested in another quantity, which is the total collision frequency. That was a single collision frequency, but I'm also interested in knowing how many collisions are occurring in the entire gas, right, per unit time, the total collision frequency. And you know why I'm interested in that number? I'm interested in that number because that's going to be the upper limit to any reaction rate. Hey, you know, a reaction in the gas phase or in solution, reaction can't happen any faster than the molecules collide. They got to collide before a reaction's going to occur. So the total collision frequency, the importance of that number is that it is the upper limit to a reaction rate. All right? So let's calculate that. Z. Well, that's going to be equal to the collision frequency of one molecule, Z1. Okay? Times the total number of molecules in the gas, N. That's what N stands for. But now, since each collision involves two molecules, I'm going to have to multiply this by 1/2. Otherwise, I'm going to overcount the number of collisions because each collision involves two molecules. So the total collision frequency here is 1/2 times N times Z1. Okay? And therefore, if I go and I plug in my expression for Z1 and N and simplify things, my total collision frequency here is 1 over the square root of 2 times N times rho pi d squared times the average speed. That's my total collisions per second. Okay? Now, this is not rocket science, right? This is easy. And what I want you to realize is that you do have to understand what N is, what rho is, what D is, what V bar is. I'm always surprised on an exam where this is, you know, we're going to give you this equation. I'm always surprised when students don't actually know what rho is, or N is, or V is, or D is, okay? So this is easy. You do just have to understand this is the total number of molecules in the gas. This is the density of the gas in molecules per cubic meter, the diameter of the molecule, the average speed. All right, that was just a helpful hint. Okay, so this is the upper limit to the reaction rate. So now, when somebody tells you the rate of this reaction is, you know, so many molecules per cubic meter per second, what you can do is a back of the envelope calculation to see whether or not they're telling you the reaction rate is greater than this number. If it is, you can say, aha, got you. Can't possibly be, okay? Really important. We call this, right, if a reaction has this rate, it will mean that the probability of the reaction occurring is 1, all right? The reaction has that rate, we call that the gas kinetic rate. That's a term that we also use. All right? Okay. And then finally, one other quantity from the gas kinetic theory. Yes? Yes, she asked me, what velocity here would you use? You actually are going to, in that particular case, have to take the average of the average velocities, okay? In other words, if you had two different molecules that were reacting for this average velocity here, you're going to have to use the average of the average velocity, okay? And then your error bars on the experiment will always be large enough to take that into consideration. Okay, good question. Okay? Okay. one other quantity, and that is something called the mean free path. What I want to know here is, on the average, how far does a molecule travel in the gas before it suffers a collision? That's what a mean free path is. A mean free path in solution. Sometimes if you do a solid state physics course, you'll hear about the electron mean free path. A mean free path is always the distance traveled between collisions. That's what that is. And we're going to call it lambda. So this isn't wavelength anymore. We just changed our definition of lambda. Lambda here is the average distance between collisions. Okay, so how are we going to calculate that? Well, what we're going to do is we're going to take the average distance that a molecule travels per unit time, per second, and we're going to divide it by the number of collisions that occur per second. And you're going to see that the per seconds are going to cancel here, right? So we're going to have the average distance per collision. That's what we're after. Well, this is easy to do because the average distance traveled per second is simply the average velocity, right? It's meters per second. That's the average distance traveled per second. The number of collisions per second that happen, well, we just calculated that. That was Z1. That's Z1. So we can substitute in Z1, V bar. V bar cancels, okay? And what we're left with is 1 over the square root of 2 rho pi d squared. That's meters. That's the average distance the molecule travels per unit time, or per unit, average distance traveled per collision. Okay? So this is another generic quantity useful in many cases, also in other kinds of cases that I just mentioned in solid state physics. Okay, so what I want to do now is that we said we were going to start talking about the motions of molecules. So we've taken care of now the translational motion. And now I want to start talking about the internal degrees of freedom. And let's do that. Let me just see if I have something here now. Okay. Let me raise the board here. Okay. So we've talked about this molecule, which is, a set of atoms that are bonded together. And as we always say, they're bonded together for the mutual comfort of their electrons. And we saw that it isn't frozen. It moves. It has kinetic energy. It has velocity. The velocity generates this macroscopic property, the pressure. But molecules also jiggle, right? So for example, we're going to take here nitrogen, triple bond. That triple bond actually functions like a spring. We can think of that bond as a spring between the two atoms. That spring can stretch. That spring can compress. When we tell you the equilibrium bond length of some molecule is some number, what that is the equilibrium bond length. It is not the bond length when the molecule is stretched. It is not the bond length when the molecule is compressed. This motion is the vibrational motion of the molecule. So we have that kind of internal motion in a molecule. The molecules also tumble. For example, let's take our nitrogen molecule again. Well, that nitrogen molecule, it rotates around an axis going through the center of mass. It rotates around this axis, all right? This nitrogen molecule also rotates around an axis here perpendicular to the board. It rotates in that direction. So this is the rotational motion of the molecule. All right. So the different ways in which we can have this motion, those different ways are called modes. This is a rotational mode. This is a vibrational mode. We didn't use the word before in talking about translation, but those are translational modes. Right? Sometimes we also call these modes degrees of freedom. Okay? So a molecule has translational modes or degrees of freedom, vibrational degrees of freedom, and rotational degrees of freedom. Now, in general, if you have an N-atom molecule, you've got 3 N total modes. All right? When I say total modes, that means the sum of translation, rotation, and vibration. Okay? Of those 3 N total modes, 3 of them are translational modes. Why do we have 3 translational modes? We have 3 translational modes because we're operating in a 3-dimensional space. So if we have some molecule here, right, that molecule has motion in the x direction, in the y direction, and also in the z direction. Those are the 3 translational modes of the molecule. Well, what that means then, if 3 of the modes are used up, then for translation, then we must have 3n minus 3 internal modes. Right? 3n minus 3 must be the number of modes that is left over for the internal degrees of freedom, for rotation, right, and also for vibration. Okay. And what we're going to see next time is that these internal degrees of freedom, these internal modes, they're going to be quantized. That is, this molecule is going to be able to vibrate with only certain amounts of energy. There's going to be a ground vibrational state. There's going to be a first excited vibrational state, a second excited vibrational state. Just like we talked about the energy levels of a hydrogen atom, where the electron was bound with different amounts of energy, is dictated by a principal quantum number, the vibrational degree of freedom is also going to be dictated by a quantum number, a vibrational quantum number. In addition, the rotations of the molecules, they are also quantized. So a molecule is going to be able to rotate with only one energy, or another energy, or another energy, but not any energies in between. There are discrete rotational states. We're going to be talking about another kind of quantum number. In that case, a rotational quantum number. That's where we're going to pick up on Monday. See you then.